All right, guys, it is 10 o'clock, so we're going to get this thing started. Thank you guys for being here. This is the week 3 content review for AP Physics 1. I'm Matt Dean. I work with A Plus College Ready, and we're going to try to make sure that you understand vectors and a little bit with projectiles today. Will you guys, somebody please unmute your mic and just let me know that you can hear me and that you can see my screen.
Yes.
All right, thank you. All right, so as you can see on the screen, please keep your mics and webcams turned off. If you have a question, unmute, ask a question. We want you to ask questions. We are recording this session, and the session will be posted to the A Plus College Ready, and that should say A Plus College Ready Science YouTube channel. It's really easy to find, just A Plus College Ready Science. If you search for that on YouTube, you'll be able to find it. We'll have a similar session next week. It will be on Friday, week from today at 10 o'clock. And it's going to cover projectiles that are shot up at an angle other than horizontal. So that one will be a little tougher session than today's session. I think you'll find today's session is pretty straightforward. All right, here we go. So first of all, we're going to talk about two types of measurements, scalars and vectors. A scalar is a measurement or a physical quantity where only magnitude or size matters. Doesn't include direction. So common scalars that we'll talk about in physics include speed. When we talk about speed, we're just talking about 20 miles an hour. We're not concerned with which direction it's going. Distance. If we're talking about how much distance we walk or travel, 40 meters, 80 feet. We're not concerned about the directions we went when we're dealing with scalars. Vectors, on the other hand, are measurements or physical quantities that take into account both the size, the magnitude, and by the way, magnitude is the word they're going to use on the exam, the physics exam, but also direction. So size and direction, magnitude and direction both matter when we're talking about vectors. So the vector version of speed is velocity. If we're talking about velocity, it might be 20 meters per second to the right, or 20 meters per second north, or you might just say plus 20 meters per second, or minus 20 meters per second. Remember that in physics, plus means either to the right or up, depending on if you're going vertically or horizontally, and minus means either downward or to the left, depending on your frame of reference. So instead of saying a direction, we might just see plus and minus. Displacement is sort of the vector version of distance. So displacement is when you might, if you walk, we'll look at an example of displacement in a minute. Let's just hold off on that. Acceleration is also a vector. Remember that if you have a positive velocity and a negative acceleration, that means that you're slowing down. On the other hand, if you have a negative velocity and a negative acceleration, that means you're speeding up. Whenever the velocity and acceleration have the same sign, which means they're acting in the same direction, speed increases. Whenever the velocity and acceleration have opposite signs, that means they're acting in opposite directions, the object is slowing down. So let's look at the simplest cases of vectors. Let's look at vectors when they're in one dimension. So you have two or more vectors that are both acting maybe horizontally or maybe both acting vertically. So here's a simple example. Tom walks 20 meters due east and then walks 30 meters due west. What is his displacement? First of all, let's say the question it asks what distance does he travel? Remember, with distance, a scalar, direction doesn't matter. So if he walks 20 meters due east and 30 meters due west, his distance traveled is 50 meters. But in this case, we're asking for displacement. Displacement is a vector. Direction matters. So he goes 20 east, and that's not east, that's west. He goes 20 east, and then he turns around and goes 30 west. You simply add those together, remembering that left, in this case, west, is negative. So I'm going to say negative 30 plus 20. We end up with a net displacement of negative 10, or 10 meters, and we would write it out with sig figs, 10 meters west, or we could write negative 10 meters. Either one of those answers is right. So essentially a displacement gives you where you ended up compared to where you started. Where you ended up compared to where you started. That's what displacement is going to tell you. Takes into account both magnitude and direction because it's a vector. Now let's make this a bit more complicated, and let's look at what happens when you have vectors in more than one dimension, in this case in 2 dimensions. So here's the problem we're going to work next. Tom walks 20 meters due east and then turns and walks 30 meters due north. What is his resultant displacement? That word resultant simply means the sum. So you're going to add them together. But since they're in different dimensions, you just can't say 20 plus 30. Okay? You've got to do what's called vector addition. And I'm going to recommend to you what I call the tip to tail method of vector addition. And we're going to go to the next slide and work this problem out. So let's say he's going 20 meters east and 30 meters north. So what I would recommend that you do is to, first of all, draw in a vector 20 meters to the east. Go ahead and label that. Then you're going to come to the tip of the first vector you drew, and you're going to start with the tail of your second vector. So tip to tail. Draw in the first vector. I like to draw in the horizontal ones first, and you'll see why here in a second. But it doesn't matter the order. Go to the tip of that first vector and then draw in the second vector. Remember, the second one was 30 meters due north. You want to try to draw them as close to scale as possible so your pictures look accurate, but it doesn't have to be perfect. Since this is 20 meters due east and this is 30 meters due north, that's a 90-degree angle, right? So now we're going to draw in what's called our resultant. This line is going to represent the sum of 20 east and 30 north. To draw in a resultant, you start at the tail of your first vector, and you draw in a line that connects the tail of the first vector to the tip of the second vector, like so. This is our R. This is our sum line. We can solve for that now, and we can solve for that using the Pythagorean theorem. So this is our R is our hypotenuse, our resultant. So we're going to say R squared equals 20 squared plus 30 squared. We're going to solve that out. So that would be R squared equals 400 plus 900, which is going to give us R is equal to the square root of 1300. R equals, let's take the square root of 1300 and get 36.1 meters. Now, a lot of people stop there and they think they've got the answer. They have the magnitude of the answer there. But remember that a vector has both a magnitude and a direction. When we're working in 2 dimensions like this, we typically are going to give the direction in terms of an angle. And the standard way of doing it is to find the angle between the resultant and the horizontal. So here's our resultant, this line. So you want to find the angle between your resultant and the horizontal, this angle. I'm going to call this angle theta. And notice I know the side opposite and the side adjacent to that angle. So to find that angle, I'm going to use tangent. Remember that the tangent function is equal to opposite over adjacent. So in this case, that would be opposite side of that angle is 30. Adjacent side is 20. So to solve for theta, I'm going to say 30 divided by 20. And I'm going to take the inverse tangent. So shift and tangent on your calculator. And that gives me an angle. And I'm going to say at 56.3 degrees. You need a little bit more than that, though. And the way you typically do that is you name the direction you're starting at. So we're going to start at the horizontal east, and we're going to go 56.3 degrees toward the north. So we're going to say this is 56.3 degrees north of east. This whole thing is our answer. Our displacement here is 36.1 meters at 56.3 degrees north of east. Before I go any further, anyone have questions on how I got that direction, what the direction means? Any questions I can answer for you about the directional component of this? All right, so I see in the chat, how did I get the angle? So I wanted to find the angle between my resultant, this line, and the horizontal, this line. So I tried to find this angle. I called that angle theta, and I knew the side opposite of that angle, 30, and I knew the side adjacent to that angle, 20. Tangent is equal to opposite over adjacent. So trig function equal to opposite over adjacent. So I said the tan of theta is equal to the opposite side, 30, over the adjacent side, 20. I did in my calculator 30 divided by 20. And then to solve for theta, I did the inverse tangent, shift and tangent on my calculator. Shift, tan. And I ended up with a degree of 56.3 degrees. Does that make sense? All right, well, let's see what we can do with this now. So here's another problem. Tom walks 20 meters at 30 degrees north of east, and then turns and walks 30 meters at 45 degrees south of west. What is Tom's resultant displacement? So to work a problem like this, the best way to do it is to use what's called vector resolution. So when we have vectors that are at odd angles like this, the first thing that we're going to do is to take each of those vectors and break them down into horizontal and vertical pieces. We call those components. And the process of breaking them into those horizontal and vertical pieces is called vector resolution. So let's look at what we've got here. I want to go to a slide where I can work this out. So here's my problem. First thing I'm going to do is to draw in the first vector. He's walking 20 meters at 30 degrees north of east. So I'm going to draw in a horizontal, and that's not really horizontal, but it's good enough for right now. And 30 degrees north of east would be something like that, where this angle is 30, and the displacement here is 20 meters. And I'm not going to worry about sig figs until the end of the problem. So when you have this vector like so, to break it into components, you're going to come to the end of the vector and draw down a vertical. So you make this be a right triangle. This component is going to be the vertical component of your vector, and this side of the triangle is going to represent the horizontal component of your vector. To find those, we can use trig functions. If we wanted to find the x side, that x is adjacent to 30. So we could use the cosine function. Cosine 30. Cosine is equal to adjacent, in this case, x, over hypotenuse, in this case, 20. So if we solve that out for x is equal to 20 times cosine 30. So let's calculate that in our calculator. Cosine of 30 times 20. We end up with x of 17.3. All right, so now we want to do the same thing with the vertical component. To find that, we're going to use sine, because sine is opposite over hypotenuse, and this y is opposite of our 30-degree angle. So we're going to say sine 30 equals y over 20. Solve for y. So y is equal to 20 times the sine of 30. And when we do the math on that, 20 times the sine of 30, we end up with 10. It's going to be meters. So we can see from our picture that this x is 17.3 meters, that's east. And the y is north, up. So that's the first picture, the first vector broken into vertical and horizontal components, those two. Now we need to do the same thing with the second vector. So the second vector was 30 meters at 45 degrees south of west. So drawing a horizontal. South of west would be over this way, because here's west. This would be 45 degrees. And this is 30 meters. Just like we did last time, the first thing to do is to draw in a vertical like so. Make that into a 90-degree triangle. We want to find a horizontal and a vertical component. So to find our horizontal component, our x, we're going to use cosine. We're going to say the cosine of 45 equals our adjacent side x over our hypotenuse of 30. We're going to solve for x by multiplying both sides by 30. Cosine 45 times 30 is going to equal to x. So x is equal to 21.2, and that is to the west. All right. We're going to do the same thing with the vertical. To find the vertical, we're going to use sine. Sine of 45 equals opposite, which in this case is y, over hypotenuse of 30. We're going to solve for y. Y is equal to the sine of 45 times 30. Y in this case is also equal to 21.2 meters, but the y is headed south. All right, so now we have both our vectors broken into vertical and horizontal components. Now we're going to combine our horizontal components with each other and our vertical components with each other. So let's start with the horizontal ones. 17.3 east and 21.2 west. So remember, west to the left is negative. So we're essentially combining negative 21.2. East to the right is positive, and positive 17.3. If we combine those together, we end up with negative 3.8, or 3.8 west. All right, now we need to do the same thing with our vertical component. So we've got 10 north and 21.2 south. So we're going to combine those. Remember, south in this case is negative. So essentially we're combining negative 21.2 and positive 10. So we end up with a negative 11.2, or 11.2 meters south. So now we've taken our vertical and horizontal components from each of the two vectors, and we've combined them together to get this. Our final step is to take these two components and put them back together to get a resultant displacement. So let me make a little space here on my screen. So now we're just going to do straight up vector addition. We're going to draw in our horizontal vector, which is 3.8 to the west. We're going to do the tip to tail method of vector addition. So we're going to come to the tip of this first vector. We're going to draw in our second vector, which is 11.2 to the south. We're now going to find our resultant by connecting the tip of the first vector, the tail of the first vector to the tip of the second one. That's R. That's our resultant. And we're going to solve for that resultant by using Pythagorean theorem. So R square equals 11.2 square plus 3.8 square. We do the math on that. Solve that out for R, and we end up with 11.9 when we solve that out for R. Now, what you got to remember is that that's just part of the answer. That's the magnitude part. This is a vector. We have to find a direction. And remember, the direction that we want to find is the angle between our resultant, and the horizontal. which would be right here. So to find that angle, the easiest way to do it is to use the tangent function. We're going to call this angle theta, and we're going to say that the tangent of that angle, theta, is equal to the opposite side of that angle, which would be 11.2, over the adjacent side, 3.8. We're going to go 11.2 divided by 3.8. And then we're going to take the inverse tangent. We're going to hit shift and tangent on our calculator. And we're going to end up with an angle measure of 71.2 degrees. And our direction here would be south of west. So our complete answer on this question is 11.9 meters at 71.2 degrees south of west. So it took a lot of steps to get there. When you have vectors like this that are not horizontal or vertical vectors, break them into horizontal and vertical components first. Combine the horizontal component of the first one with the horizontal component of the second one. Do the same thing with the vertical components, and then add those sums together to get a resultant, in this case, a resultant displacement. All right. So now let's get to the main topic for today, which is projectiles. So a projectile is any object that once it's projected, it's shot out or dropped. It continues in motion by its own inertia and is influenced only by the downward force of gravity. Now that's assuming that we're ignoring friction and drag, which in AP Physics 1, we almost always do. So we ignore air drag and friction in these problems, so that the only force acting on these projectiles is the force of gravity, which we know is acting downward, straight down toward the earth. A trajectory is the path a projectile follows, and the range is the horizontal distance or displacement traveled by that projectile during its flight. So those are important terms. Projectile is the actual object that's being shot out. The trajectory is the path it follows, and the range is the horizontal distance or displacement that it travels. So let's look at a sample problem here. Matthew throws a ball horizontally with an initial velocity of 20 meters per second to the right from the edge of a cliff that is 50 meters tall. How long does it take the ball to reach the ground? What range does the ball cover during this trajectory? And what is the ball's resultant velocity before it touches the ground? All right, so when the problems we're going to work today are all going to be these horizontal projectile problems. Next week, we're going to shoot some up at angles with the horizontal. Today, they're horizontal problems. So when you do this, when you work in any kind of projectile problem, whether it's horizontal or not, you need to think about this as a vertical piece of the problem and a horizontal piece of the problem. And you need to keep those separate. During projectile motion, the horizontal velocity remains constant. And the reason it remains constant is that there's no force acting horizontally on this object. The only force acting is gravity, and it acts vertically, not horizontally. So that 20 stays at 20, the horizontal velocity. Now, what we're not thinking about here is vertically, since this thing is shot horizontally, the initial vertical velocity is 0. And as soon as that thing leaves the person's arm, it starts to accelerate because gravity is accelerating it. And it's accelerating at the acceleration due to gravity, which is -10 meters per second square. It also eventually is going to fall a vertical distance of 50 meters. Well, that means that its displacement vertically, which we're going to call delta y, is -50 meters. You got to use that negative because it's 50 meters down. It's falling 50 meters. All right, so part A here, how long does it take the ball to reach the ground? Well, you've got to think for a second about what's determining the time. Is it horizontal or vertical stuff that's determining the time. And I hope you see that it's the vertical stuff that's determining the time because it's following a vertical distance. So when we're calculating time, we need to think vertically. And the way we're going to do that is we're going to go to one of our kinematic equations. The easiest one to use would be this one. Delta y equals VOT plus 1/2 AT squared. Now, you might see this listed as delta x. We're using y here because we're working vertically. We would use x if we were working horizontally. Same equation. Remember, we're only thinking about vertical stuff for right now. The initial vertical velocity, this component is 0, which means this piece goes away. We're looking for time. I like to go ahead and solve my equations for the variables I'm looking for before I put the numbers in. And I think that would be a good habit for you guys to get into. So we're trying to find time. So let's first of all multiply both sides by 2 to get rid of this 1/2. Let's then divide both sides by a to get rid of that a. And then we've got t squared is equal to this. So let's take the square root of both sides. So the square root of 2 delta y over a is going to be equal to t. Well, let's plug in what we know. 2 times delta y. Delta y is the vertical displacement, which is negative 50 meters. And our acceleration is the acceleration due to gravity, which is negative 10 meters per second squared. Well, these meters are going to cancel, and we're going to be left with units of seconds squared. Let's go 2 times negative 50 to get negative 100. Divide that by negative 10 to get negative 10. We're going to take the square root of negative 10. I'm sorry, the square root of positive 10 to get 3.16. And that's going to be 3.16 seconds because we're taking the square root of seconds squared. So to find the time in a projectile problem, the time is dependent on vertical stuff. Work vertically to find time. Now, on part B, we're looking for the range. Well, the range is the horizontal displacement. So for range, we need to think horizontally. And let's think about what we know horizontally. We know the horizontal velocity is 20. So let's make a column here for horizontal. So the velocity is 20 meters per second. There's no acceleration because there's no force acting horizontally. And that's pretty much what we know, right? We do know, though, that we found the time over here to be 3.16 seconds. Well, that time is the time for both the vertical movement and the horizontal movement. Because this ball is moving at a constant horizontal velocity, we can use this equation to find its range. Delta x equals VT. That equation always works when you're talking about constant velocities. So the displacement, the range in this case, is equal to the horizontal velocity times the time, which in this case would be 20 meters per second times the time of 3.16 seconds. So we end up with a horizontal displacement of 63.2 meters. And that's 63.2 meters, positive 63.2 meters, or we could have said 63.2 meters horizontally. So part C is maybe the trickiest part of this equation or question. What's the ball's resultant velocity before it touches the ground? Well, remember, this ball started off moving only horizontally. But as soon as it left the guy's hand, it started to accelerate vertically. So it eventually has vertical speed and horizontal speed. This is asking us to add together the horizontal and the vertical speeds. So we're going to do a vector diagram. We're going to draw in our horizontal speed first, 20 to the right, 20 horizontally. What we don't know is what's the vertical speed. And we're going to have to calculate that. We know we start off with a vertical speed of 0 and that we accelerate at negative 10. So let's use this kinematic equation right here. V equals VO plus AT. And let's use that to solve for the final vertical speed. So V is going to be equal to 0, the initial vertical speed, plus acceleration, negative 10 meters per second square, times time, which we found to be 3.16 seconds. Multiply that out, we get a final vertical speed of negative 31.6 meters per second. So now we need to use vector addition, tip to tail method, to add our horizontal speed 20 to our final vertical speed of negative 31. So let's come to the tip of the first vector and let's draw in the second vector, 31.6. To find our resultant, we're going to connect the tail of the first vector to the tip of the second one. That's our resultant. That's our R. So now we're going to do a little Pythagorean theorem, and we're going to say R squared equals 20 squared plus 31.6 squared. Let's do the math on that right quick. So we end up with an R of 37.4 meters per second. Now, a lot of you would stop there and think you're done. You got the magnitude of the final velocity, or maybe the speed of the final velocity, but you need an angle. You need a direction. This is a vector. And remember, the direction that we want to find is the direction between our resultant and the horizontal. So that angle. To find it, we're going to use tangent. And we're going to say the tangent of our angle, theta, right here, is equal to the opposite side, 31.6, over the adjacent side of 20. We're going to go 31.6 divided by 20. And we're going to take the the shift and tangent, the inverse tangent of that. And I just messed up on my calculator, so let me try that again. 31.6 divided by 20, and then hit shift and tangent. And we end up with 57.7. Now here's the deal. This question doesn't tell us north, south, east, west. So our answer is 37.4 meters per second at 57.7 degrees. You still need to describe which way it's going. So the easiest way would be to the right and below the horizontal. So our answer here, 37.4 meters per second at 57.7 degrees to the right and below the horizontal. Or you could have drawn your picture to the left. It says to the right. So yep, to the right and below the horizontal. So when you're calculating a resultant, you've got to have a magnitude, which in this case is 37.4, and you've got to have a direction, which in this case would be 57.7 degrees to the right and below the horizontal. All right, so that's a horizontally launched projectile. We're going to see several more examples of samples of those as we go here. We're going to start off easy, though. Here's problem 1. So Joe walks 10 meters north. He then walks 8 meters south. He turns and walks 12 meters west. And finally, 8 meters due east. What distance does he travel? Notice this is distance. And remember, distance is a scalar. Direction doesn't matter. So if we're looking for distance, we just add all these up. He goes 10 plus 8 plus 12 plus 8. And let's see, that's 38 meters. So his total distance traveled is 38 meters. And that's as hard as that gets. Now let's twist it a bit. So this looks sort of like the same problem, but in this case, it's asking for what's his displacement. And remember that displacement is a vector, and it takes into account both magnitude and direction. And essentially, it's going to tell you where you end up compared to where you started. To work this problem, let's combine our north-south components with each other, and let's combine our east-west components with each other. So let's first of all take 10 north and 8 south and combine those together. So we'd have 10 going this way, and we would have 8 going this way. And I'm hoping that you see when you combine those, you end up with 2 to the north. Positive 10 plus negative 8 is positive 2. So we've got 2 meters north. Let's do the same thing with our horizontal components. We've got 12 west, so that would be negative 12, and 8 east, positive 8. When we combine negative 12 and positive 8, we end up with negative 4, or 4 meters west. Once we combine the vertical components together and the horizontal components together, now we're going to take these two pieces and use vector addition to add them. So I'm going to put in my horizontal component first of 4 west. I'm going to go to the tip of that vector and draw in my second one, 2 north. I'm going to go to the tail of my first vector, connect that to the tip of my second vector to find my resultant. Let's use the Pythagorean theorem. R squared equals 2 squared plus 4 squared. Add those together, solve for R. R comes up to be 4.47. And again, a lot of you would stop thinking you got the answer. But displacement is a vector. It requires a direction. And remember, the direction we want is that angle between our resultant and the horizontal. That angle right there, we're going to call it theta. And to find that angle, let's use tangent. So tangent of our theta is equal to the opposite side, which is 2, over the adjacent side, which is 4. So we're going to go 2 divided by 4. And we're going to take the inverse tangent, shift tangent on our calculator, and we're going to end up with 26.6 degrees. And in this case, that would be north of west. So that is our complete answer to problem 2. We've got our magnitude of 4.47 meters and our direction of 26.6 degrees north of west. All right, so now let's look at another horizontal problem, a horizontal projectile problem, rather. Samuel throws a 10-kilogram ball horizontally from the edge of a 100-meter tall cliff with an initial velocity of 20 meters per second to the right. How long does it take the ball to reach the ground? So we're looking for a time. That's important. What you've got to be able to filter out here is that in this case, you're given some extra information. In these projectile problems, you don't need a mass. You're given this mass. You don't need to know that. That's extra information. Remember that when we're working these problems, the time is determined by vertical pieces of the problem. So let's think vertically. He throws the ball horizontally at 20 meters per second to the right. I'm going to keep a horizontal column over here too. Vertically though, since he threw it horizontally, its initial vertical velocity is 0. As soon as it leaves his hand, it begins to accelerate at the acceleration due to gravity. And this thing's going to have to go a vertical displacement to get to the ground of negative 100 meters. Remember, it's got to be negative because it's going down. It's falling. So we can use vertical pieces to find time. And the easiest way to do that is to use this kinematic equation. Delta y equals VOT plus 1/2 AT squared. Just like we did last time, we're going to solve this for time, remembering that the initial vertical velocity was 0. So this whole piece goes away. Multiply both sides by 2 to get rid of this 1/2. Divide both sides by a to get rid of that. And then take the square root of both sides to get rid of the t square. So that's our equation solved for time. And now let's plug in what we know. So our delta y is negative 100 meters. And our acceleration is -10 meters per second square. And we're going to solve that for t. So we're going to end up with -200 on top divided by -10 on the bottom. That's going to give us +20. We're going to take the square root of +20 to end up with a time in the air of 4.47 seconds. So that's our answer on this one, 4.47 seconds. That's the total time in the air. Now, on the next slide, we're going to get another take on this problem. In this case, it's asking us, same problem, it's asking us to find the range. Well, remember, the range is the horizontal displacement. So in this part of the problem, we've got to think horizontally. And what we know horizontally is that we've got a speed, a constant speed that doesn't change throughout the whole problem of 20 meters per second. We've got an acceleration of 0 because there are no horizontal forces acting on this object. And the time in the air is the same as it was for the other way, which was 4.47 seconds. When you're calculating a horizontal range in a projectile problem, here's what you're going to use. Delta x equals VT, which is really just this equation. Because remember, acceleration is 0 horizontally, so that goes away. So that's how we came up with this equation. So our delta x is equal to our horizontal speed of 20 times our time of 4.47 seconds. Multiply that out, and we end up with a displacement in this case of 89.4 meters. And we should say, we could write positive at 89.4, or we could say 89.4 to the right. But we do need a direction because displacement is a vector, needs a magnitude and a direction. All right, so we got one more take. I actually got two more takes on this. So next, what is the ball's vertical velocity at the instant before it hits the ground? Well, remember what we knew vertically. Sam, what you need?
That can touch the blade of a lightsaber and can have a snack.
Okay, yes. All right, so vertically, here's what we know. We know our initial vertical velocity, 0. Our acceleration due to gravity, -10 meters per second square. We know our vertical displacement, -100 meters. And we know the time in the air was 4.47 seconds. We're trying to find how fast was this ball going the instant before it touched the ground. The easiest way to do that is to use this kinematic equation. V equals VO plus AT, where V is the final velocity. VO is the initial velocity, which was 0 because we're talking vertically here, plus our acceleration, our vertical acceleration, -10, times our time of 4.47. So our vertical velocity at the instant the ball touches the ground is -44.7 meters per second. All right, I think we've got one more take on this. So next, what are the ball's vertical and horizontal components at t equals 2 seconds? Well, here's what you got to think about. Horizontally, remember, the velocity doesn't change because there are no horizontal forces acting on this ball. So the horizontal velocity started off at 20, and therefore at 2 seconds, horizontally, this ball is still going 20 meters per second. And we're going to just say plus 20, 20 to the right. Vertically, though, this thing is changing. We started off with a vertical velocity of 0. We're accelerating at -10. And in this case, we're doing that for a time of 2 seconds. So we can calculate a vertical component by saying V equals VO plus AT. So V is equal to a vertical velocity of 0, initial vertical velocity of 0, plus an acceleration of -10 for 2 seconds. So after this ball has fallen for 2 seconds, it's moving vertically at -20 meters per second. It's moving horizontally at +20 meters per second. So our answer in this case would be horizontal component of +20, vertical component of -20. And I think we have one more twist on this problem. And here it wants to know what is the resultant velocity at t equals 2 seconds. Remember, at 2 seconds, horizontally, we had +20 meters per second. Vertically, we had -20 meters per second. We want to know the resultant, which means add them together. So to do that, draw in the horizontal vector first, 20. Go to the tip of that vector, draw in the second vector, -20, 20 down. Remember, the negative doesn't really mean negative, it just means down. Find the resultant by going to the tail of the first vector, connect it to the tip of the second one. That's our resultant, our sum. So R squared equals 20 square plus 20 square. So R is going to equal to, let's do the math on this. That would be R squared equals 800. R is equal to the square root of 800, which is 28.3 meters per second. Now, again, some of you are going to stop, but you can't, because you're looking for a vector quantity, which needs a magnitude, which we now have, and a direction, which we don't have. The direction is the angle between the resultant and the horizontal, that angle, theta. Find it by doing tangent. So we're going to say the tan of theta equals opposite 20 over hypotenuse 20. So let's go 20 divided by 20, shift and tangent on our calculator, and we end up with 45 degrees. So our answer is going to be at 45 degrees. And in this case, it would be to the right and below the horizontal. So our answer on this problem, 28.3 degrees at 45 degrees to the right and below the horizontal. All right, we got one more problem, 2 pieces of it that we want to look at, and then we're going to call it a day. So Justin wants to cross a 925 meter wide river. His boat's velocity is 28 meters per second due east across the river with respect to the water. The water in the river flows due south at a rate of 6 meters per second. If Justin keeps the boat pointed directly at the opposite bank for the entire trip, how long does it take him to cross the river? So let's say here's our river. It's 925 meters from side to side. Justin starts off over here. He keeps his boat pointed straight horizontally across the river, and he can travel horizontally 28 meters per second. And we want to know how long it takes him to cross the river. Well, it turns out that if he's just going across the river, a horizontal thing, this vertical piece doesn't really matter. As long as he keeps that boat pointed straight across, he's going to go at 28 meters per second across, and he's crossing this far. So we can solve for time using delta x equals vt. We're looking for time, so t equals delta x divided by v, which in this case would be he's going 925 meters across the river at a speed of 28 meters per second. That's telling me that it's going to take him about 33.0 seconds to cross the river. Now, where the 6 comes in is in the next part of this problem. So notice this looks like the same problem. But this says, how far down the river due south does he travel before he reaches the opposite bank? Don't know why that river's there. So as he's crossing the river itself is pushing him south at this speed. So if we want to know how far south he goes, we can use delta y equals vt. And again, delta y is what we're looking for. So he's traveling in the y direction at 6 meters per second. And he's doing that for the same amount of time it took him to cross the river, which was 33 seconds. So if we go 33 times 6, we end up with 198. Now, let's say that I ask you, this is not part of the problem, but let's say I ask you, what was Justin's resultant displacement? What was his resultant displacement? Let me find a place where I have some empty space. Let me just put in a new slide here. All right, so we're asking for his resultant displacement, and we've got to remember that he went across the river 925 meters, and he went down the river 198 meters. So cross river, and I've already forgot my numbers, 925, and down river 198. So if we want to find his resultant displacement, we have to combine those two. So 925 across, draw in that first vector. They're vectors, so we have to add them with vector addition. So we go to the tip of the first vector, draw in the second one, connect them, tail of first vector to tip of second, solve for r. So r squared is going to equal 925 square plus 198 square. Let me do the math. So r equals 945. Actually, it would be 946 when we round it off meters. And remember, that's just the magnitude. We need a direction. So we need to find the angle between our resultant and the horizontal. We'll find that using tangent. Call this theta. So tangent of theta is equal to opposite 198 over adjacent 925. 198 divided by 925. Take the shift tangent, and we end up with 12.1 degrees. And in this case, that would be south of east. So our answer for our resultant displacement, he actually travels 946 meters at 12.1 degrees south of east. All right, that's it for our problem today. We'll do this again next week, 10 a.m. And we'll be looking at next week, what happens if you take let's say an arrow and you shoot it at maybe 30 degrees and you shoot it with a speed of 50 meters per second. And we're going to want to know things like, how high does this arrow go? What's its range? How long is it in the air? What's its vertical velocity at 2 seconds? What's its horizontal velocity at 3 seconds? So we're going to get asked all kinds of questions about this initial setup. And that will be the main thing that we'll work on next week. Any questions before we call it a day today? All right. Well, I thank you guys for being here, and I hope to see you next Friday at 10 a.m.